Basically, in complex analysis, you have two basic things. It means like complex differentiation and analytic function, and also you have something called a residue theorem. It is used to derive something like Taylor theorem. So basically, for real functions, you discuss something like this. It means real to real functions, right? Let's say fx. Let's say something like x squared plus one or something. Then you plug in any real number x, then you can have a real number for fx. So you mean the function value. For these things are you called actually a real functions. So in complex analysis, actually we did this actually using real analysis. So we evaluated limits and we evaluated derivatives and we evaluated integrals and so on also to this real to real function. In complex analysis, what we're doing is we describe this kind of functions. It means our function now this is a complex number. And this value also can be a complex number. Okay. It means what we are going to do is actually things we do for these real to real functions, we're going to generalize this into a complex to complex function. It means complex to complex function because we know we can write an complex number as x plus iy. We call this a real part and this is imaginary part. So what we are going to do is actually we're going to generalize these things to these particular operations. So in just case of limits, let's say if we write x goes to a f x l, actually I think you can watch my limit video if you don't clear it. So we have this definition for all f greater than 0, the x is delta greater than 0 such that 0 greater than x minus a greater than less than delta, which is implies fx minus l less than epsilon. It means, let's say you can get something like this. Let's say in this definition means actually if you get some function, let's say x, and you get some sort of x value function and you have this sort of function fx, and you have some neighborhood around this a. This is a plus delta and this is a minus delta, which is your function value is oscillating around some limit a. So this is what you do for real functions. So what if I say I'm going to do the same thing, let's say z go to z naught, fz equal to some za. How are you gonna generalize this idea to this? Let's say, what does this mean? We know this portion represent distance between a comma x in the complex in the real number, because if you have some real number, if it's x and this is a, this distance is equivalent to x minus a magnitude. So this thing is also equivalent to the distance between the value L and your function value. So what we are going to do is we need to generalize this idea from real numbers to the complex plane. So it means now there's a problem arises. So we have our imaginary axis and we have our real axis. Now, if we get some complex number, let's say Z1 and Z2, how are I gonna get the distance between these two values? Anyone? How are we gonna get the distance between Z1 and Z2? I need to find the distance. How can I get? Anyone? In A levels, we do that. In A levels, we know is any 2 points, we can get the distance between any 2 points on the organ plane using this thing. We get the difference between the two complex numbers and they get the magnitude of it. So I'll write a similar definition like this. For all epsilon greater than 0, there exists a delta greater than 0 such that 0 to z1, let's say z minus z0 less than delta. This will imply our fc minus za less than epsilon. This means nothing but we can find, let's say this is my z0 point. I can find some neighborhood around this z0 point such that if I put any value in from this neighborhood to my function, it will give my function values in such a way that I'll draw another complex plane. This is real and this is imaginary. And this is my ZL. Your function value will reside only this circle, a neighborhood around ZL. So what is the problem when you comparing, right? What is the problem when you comparing this guy to this guy? What is the problem? Tell me. What is the problem? Anyone? Anyone? Here, you have two ways to approach A. It means you have this way and you have this way to approach it. But in argon plane, how many ways you can? You can come in this way, you can come in this way, also you can come in this way, you can come this way, or we can come something like this. Anyway, you can come to this. It means it doesn't matter how you come. Okay. It means to the Z naught point, if you want to arrive at Z naught, there are infinite number of ways because this is because in latter case, in the real number case, we only have this axis. So either we can go this side or this side. But here we have 2 degrees of freedom. So we are in a plane. So we can go here and here anyway like this. So to our limit to x is, it doesn't matter how we come to this point, this value should reside in some sort of neighborhood. It means if we can define a neighborhood around this Z naught within a delta radius, okay, it means, so if you take any Z value and plug into my function, the function value should reside in my Z delta neighborhood. That's the main idea. So actually, these type of limits and evaluating this proving is very difficult. So we are not going to do that. So most of probably what we'll have is actually we define basic limits. Let's say if we have something like Z goes to Z naught, Z n is equal to Z naught n. This is actually we normally know some continuous function. Actually, it is also given into a handout, and also you can just Google it. Basic function of limit. It's basically like limits you did for your A levels for the real functions, most of the time polynomials, and we know the very nice functions. We define the limits and we write any of our function, our wanted function, desired function as a summation of these nice function or like combination of these functions, and we evaluate the limit. That's what we normally do. Okay, got my point clear? You know that actually this idea is enough here because I tell this idea because I need to explain about what this analytic function means. Okay, so this is okay, fine. Hello. Hello. Fine.
Yes, it's fine.
Okay. So then, what about the derivative of a real-to-real function? Okay. If I take a function value, something like this, let's say x, if I want to find the derivative of this function, what would I do? I can find the derivative of or slope of this tangent line. Let's say it is f dash x. I can find f dash x in a way that limit delta x goes to 0, fx plus delta x minus fx divided by delta x. So what is this summation means? It means I take some point and I move some another point. Let's say I do another diagram. Let's say I just take this line. Let's say this is my fx and I move another line. This means my x plus delta x. And I evaluate my function value x plus delta x. It's my y coordinate. And I draw this line and I get the tangent of this line. It means I move delta x to one of the sides and I get the function value and I evaluate the tangent of this line. So my delta x value equating to 0 means this point is moving closer to closer. It means this tangent of this line eventually becoming equal to this tangent. So I write similar expression to my complex value function. Okay. So let's say if I consider a function like something like this, my complex plane to real function. Okay. Now I evaluate my derivative. Actually, you can extend it to the, if this is to like complex plane, you can extend this, but I take this thing because it is more familiar to. I will define something like this. My delta z go to 0 and f z plus delta z minus fc divided by delta z. Now let's visualize this in a complex plane. Okay, so I have my point z something like this. So how I move delta is a sort of distance from this point. Any idea? How can I move? How many number of ways I can have to move this input? Because these type of things you can ask, right? Because this idea is very important when you're gonna prove when a function is not analytic, right? So how are you gonna do? So it means actually you can have many ways, right? You can go something in this direction, delta is this distance, or this distance, any way you can go. But no matter how far you go, you get the delta z. It means delta z itself a complex number, right? You can have, let's say, this is z plus delta z complex number, or you can have this way because because depend on the argument of delta z, this direction will be changed. So if you evaluate this limit, you have infinite number of directions. No matter how what is the direction you go, this should lead to a same limit if your function is analytic. In other words, this f dash z is exists. Let's say if I come from this direction, I goes to this direction delta z, or I go to this direction and I will end up two difference limit. It is not an analytic function. This is the idea behind analytic function. Analytic function is simply this limit exists. This is a limit, right? Limit exists. You know, if a limit exists, limit should be unique. So then, how gonna we evaluate this thing? This is again, it is pretty much hard because if you want to show some function is analytic, what you need to do, you need to consider infinite number of these ways, and you need to prove that in any of the ways this function, this limit is exist and this is the same, and your function is analytic. So this is pretty much hard. So what we are going to do is we do some like trick. It means we assume f dash c exists. Then what will happen? Now look. Now I will take my complex plane. I got my z. Now what am I gonna do? Let's say I will get my fg is something like uxy plus ivxy. It means xy is nothing but my real part and imaginary part. So my z is x plus iy. Then what will I gonna do is I move on this direction. I can first consider only this direction. Okay. And this direction. This perpendicular two direction. Because if my f dash z is exceeds, so if I move delta z in this direction and evaluate this limit, and I move in this direction and evaluate this limit, those two should be same. It means I'm not gonna show that this limit exists. What we are going to, I'm not going to show that this limit exists. I'm assuming that this is exist. What will happen? Okay. So what we're going to do is let's say evaluate f, let's say my x plus iy minus f x plus delta x plus iy divided by my z minus this is my z plus delta x. Actually delta z, actually delta z is equivalent to delta x. If you clearly saw that, because x plus I simply add delta x, it means I can divide by this by delta x, and I set this limit delta x to 0. It means I choose specific direction, and anytime I move along this direction. Okay, it's actually, it is look like a like directional derivative. So then we can write this thing as something like this: ux plus delta x y minus a u x y, okay, divided by delta x times I times v x plus delta x times v minus v x y divided by delta x, and you send limit delta x to 0. Okay, you can clearly see that this guy is nothing but the partial derivative of u. It means we denote it as ux. This is nothing but the partial derivative of v. Okay, we denote it as vx. This is the same, but because this is a partial derivative, because we only varying x and we divided by delta x and send delta x to 0. It is like real function, right? So then what will happen? We can get this limit test. Actually, we can get limit test ux plus ivx. This thing can be given to the exam to prove this, right? That's why I'm doing, because in most of the time in your lecture, it's telling that proof will be done if the time permits. It means that if it is not time permit, the proof will be not. You can be asked, right? Sometimes it can be asked. I think probably this proof will be done because it is done first, and this will ask to our exam. Prove the Cauchy-Riemann equations. Okay. So then what will I do is I'm going to move in this direction. Now my delta z would become I delta y, because if I move y plus delta y, my z plus delta z becomes x plus I times y plus delta y. So I am adding I plus delta y to this. So I will evaluate now limit delta y goes to 0. It is become u x y plus delta y minus u y x y. Okay. I straight away write this. You can clearly see that, right? You can if z plus delta z, you can get put y plus delta y instead of y. Then you can subtract. I simply write this thing straight away. Right? Z plus delta z minus f z, right? So then you can write I times this is actually delta y, I delta y, because your delta z is equivalent to I delta y, and plus I times v x y plus delta y minus v x y divided by I delta y. Okay. So you limit delta y to goes to 0. So you simply evaluate this limit. Okay. So it is actually nothing, but you can get this limit as actually you can get 1 over I means minus I. Okay. This is 1 over I means minus I. This is actually uy plus actually this is become I to I cancelling out. It is vy. Now you have two limits. Previously you should have ux plus I v x. Okay. So in because if dash is exist, it doesn't matter we go in this direction or this direction. These two results should be equal if our derivative exists. It means our vux plus ivx should be equivalent to vy minus iuy. It means from this we get ux equals vy and vx equals minus uy. These two things we called Cauchy-Riemann equations. So this is the first thing you need to know. So I do this because I need to tell very important thing. Because this thing means in the Cauchy equation means if Z is analytic. In other words, if dash Z exists, these two hold. But there's no guarantee these two things hold. This thing hold. It means you can have Cauchy-Riemann equation. It means you can have the same limit along this direction and this direction. Still, your function can't be analytic. Why? Because it can give a different limit to these some of these directions, right? We don't know. So this is only true in this direction, not in this direction, except a few other conditions. I think it is given at your hand up. It is mean your derivatives are continuous and everywhere else, and there are some conditions. Except those conditions, you cannot directly say from if Cauchy-Riemann equations are exist, Cauchy-Riemann equations are true, you cannot directly say this thing happened except few conditions, right? It will give you inside your handbook. Please look on that because it is pretty much important, because sometimes the most probably they will give you some functions and we will evaluate your Cauchy-Riemann equations, but still it can't be analytic, or it will straight away they will ask what are the Cauchy-Riemann equations means or not, right? They can ask this proof and they will ask you to uh, show that this Cauchy-Riemann equation is satisfying, and you should have, I think, some condition. Actually, I don't remember the exact condition. It should be something like your ux and uy are continuous and everywhere else, and your function is bounded. And so there's some one or two conditions. Please look on that. Please specifically remember that, because this is the place where you can get lost, right? Because sometimes they will get some function, and if these conditions are not satisfied, you can straight away say this. But if this is given, you can straight away say this. Okay. So this is actually one of the main theorems in analytic functions. Clear? Hello? Hello? Anything you need to ask from clarify from this thing, analytic functions or complex derivative? It's nothing but you generalize the idea behind the limits and the derivative to the complex plane. There's nothing more difference. Hello? Anyone? Any problem? Please ask, right? Hello? So because the hello, Shamanta?
It's okay. It's
Okay.
fine.
So then, actually, I'm going to discuss the second two topics. This is actually you can get to your questions residues, right? Because I'm not going to discuss pretty much thing. I think there is something you need to know because I think they are straight away given you the formulas for the Taylor series and Lorentz series, and I'm going to show you how the LDCs come, because sometimes you can get messed up with these CNs, right? Because you don't know what these things are mean. So I will show you. Actually, we have Taylor series. Actually, I don't remember the exact formula for either. So you have some Taylor series. So because they have something like you have some constant term, it means FA, as I remember, FA you have, and then you have F dash A and X minus A, then you have F double dash A, X minus A, square divided by 2 factorial and so on. You can have this is a Taylor series as you have, and you have some remainder term. Actually, I don't remember the exact expression for that. But the thing is, if you want to write the Taylor series in complex domain, you need to find these f dash a, f double dash a, and so on. It means you have to find this nth derivative of your complex function. So how you're going to need to find the derivative of this function, because most of the time actually if your function analytic, let's say let's say pretty much simple function, let's say your function if z is actually z squared plus 1, you can easily give it away. This is actually 2z, right? Because if it is your function is look like a polynomial or something, you can straight away apply the derivatives rules you apply from real functions to this function without no issue, right? Actually this can be proven. I'm going to do that. But what will happen is if you want to write a Taylor series, some let's say some but like very ugly function, how you're going to need to evaluate these derivatives. So in this, actually, we think we have some lucky thing called residues, some idea called residue. It means I'll take my complex function. Okay, so let's say this is my complex functions domain and I have a hole here, and this is my complex number A. So it means in this domain, let's say this is my contour. Let's say this is my contour. So in this region, this small circle, my functions is not defined. Okay. So then I will consider the integral, let's say contour integral around this contour fc over z minus a. Okay. dc. Okay. So it means actually it is enough that your function is not defined in z equals a. Okay. It means what will happen is if let's say this, if I take this fz, let's say if fz function is analytical, right? If it is analytical, uh, let's make it clear. So fz function is analytic everywhere. Okay. It means it should be continuous everywhere. Okay. Because analytic means it is differentiable. Differentiable means it is continuous. It is continuous everywhere. So what will happen? This is continuous everywhere, and you evaluating this. It means this function is finite at this point, but you have this guy. These type of things you call poles. It means if you have something like z minus a or some kind of this, these things you call pole. Pole at a. It means if z equals a, your value is going to infinite because you have some finite value at your numerator, but in the denominator you got 0. So then what will happen? I evaluate this integral to a function where I have this pole and I evaluate integral around this contour, right? I will call this a contour integral. So what will happen? I evaluate this integral. I do a very small thing to evaluate this thing. I get a very basic contour like a circle around A around radius R. It means my function is analytic and I'm going to evaluate. I get this contour, this integral around this contour. So then I make a substitute like to my z equals a plus r e to the power I theta, because we know if I take this thing, let's say if I this angle is let's say this is my imaginary axis and this is my real axis. If I take any z on this circle, I can write z minus a as r e to the power I theta, because it is magnitude would be r and it is argument changing because when it's rotated, right? So then I can write dz over d theta. It is equivalent to a is constant. So it is r times e to the power I theta times I. Okay. So I have I r e to the power I theta. So then substitute this thing. You can get I equivalent to. So your theta goes to 0 to 2, 5 when you're going around this contour. Okay. And you will have if z in terms of f z you put a times r times e to the power I theta divided by z minus a, you simply put r to the power e I theta, and you put I r e to the power I theta d theta. Okay. So then you can straight away say these things are cancelling out. Then what you're gonna do, you evaluate this thing. To send limit r goes to 0, then you will evaluate 0 to 2, 5. Limit, you can take limit inside because r is nothing to do with the integrating variable. If a to the times r e to the power I theta times d theta. You can straight away say in this I here because I can take I out. So then you can straight away say this thing will become FA. Okay. So it means you can straight away put this thing is 0 to 2, 5 and you can take FA out 1 d theta. And you can have this thing is 2 phi I f f a, right? 2 phi I have fa. So this integral, actually, I don't remember exactly what is the residue. I think it should be this integral, right? Yeah, it is a residue. This should be this integral. So you will call this integral as a residue, because you will call residue of f at a. You will call this thing as 2 phi I into the contour f z over z minus a. Okay, dc. If my z function is analytic, or if we evaluate this not evaluate, use some sort of, let's say, gz or something, right? Okay. Okay, so now you can evaluate it is gz, and you can put some geo to be clarified. So this thing you call a residue. So what will happen if this function is a form of something like fz is z minus a? It means its numerator you can have something finite value, and denominator you will have something goes to 0. It means you have 0. It means your function value tends to infinite, and your function is not defined at z equals a. So it means you have a pole at a. It means your gz is a form of, let's say, your gz goes to infinite, plus or minus infinite at z equals a. It means it has a pole of in z equals a. So this type of thing you call a residue of ga. So this thing you can prove that this guy is equivalent to g. You can think of this will be equivalent to fa if your gz is a form of analytic function divided by z minus a. If z function is analytic in all in the analytic in a, and it is defined by z minus a, which is the cause for your pole. Okay, so then you can evaluate your fa as something like this. You have something very nice full result. It means 2 phi I into the fc into z minus a in d. Actually, this is what I do. I evaluate this integral, right? I evaluate this integral, and I simply call this guy as a some function of dz, right? Because just the sake of notation, I need to introduce what is the residue is. So then what will happen? I will have some expression for my fa. What if I differentiate this thing to get f dash a with respect to a? So then I will get 2 phi I. It is no problem. I can differentiate this thing with respect to a. So I will, when I differentiate, I will get z minus a squared. It is minus 1 times minus 1, because when I differentiate z minus a, I will get minus 1 into dz. Then I will end up with is 2 phi 1 over 2 phi I into contour integral fc over z minus a squared dc. But this thing is become f dash a. Okay. Similarly, you will get, if you differentiate further, if double dash is a day, you will get contour integral 2 times 2 phi I. Just do it by yourself. F z minus a cube dc. Or also you can get f n a. You can clearly see this. You can get n minus 1's factorial. Okay, n minus 1 factorial divided by 2 phi I residue fc divided by, actually you can get z minus a n plus 1 dc. That is how you get the derivative of this function. Now we will write a Taylor series like this. Your f z is something like this. If you write a Taylor series something like this, we encounter something like this, right? F n a divided by nth factorial. Okay. It is probably, I think, yeah, you will encounter like something like this. So if it's n factorial, I think I did correct, right? So I think if double dash it is 2, no, it is this n factorial. This should be n factorial. This should be n factorial, my bad, right? Because this is 1 and this is if double dash it is 2, and if you got 3, it will multiply by 3 and it is 3 factorial. So it will be n factorial. If you evaluate this part, you will get this guy, because it is in terms of Taylor series, you will end up with fc divided by z minus a n plus 1 dc, and this is 2 phi I. This is the magic formula which is given for you to see n in your handout when they are defining Lorentz series. Okay, so remember that this is actually the coefficient of your Taylor series of the term z minus a the power to the power n. So more important thing is, let's say, this is a very nice thing. let's say what will happen, you have some function like something like this. I have some function like gc into fc divided by z minus a to the power k. So now I will evaluate some integral, something like this. I will evaluate contour integral c gc minus z minus a to the power k to the power 1 dc. I simply evaluate this integral. I convert this integral as 0 to the power c and gc divided by z minus a. So I will substitute in terms of fc divided by n plus 1. Okay, no, k plus 1. Okay, because this is k here and dc. Now what will happen? In your Lorentz series, you probably noticed that actually you can go to the handout, you will see how these minus powers are come. So now we will see if this is an analytic function, you can have like when you are evaluating, let's say you're going to evaluate this integral, like this is to the power n, right? Let's say this power n to the general case. You can get your function, you will have your fa when this thing equivalent to 1. It means your n plus k equivalent to 1. It means your n can go up to 1 minus k to infinity. That's how in your Lorentz series, you will get minus powers. Because if you have some function like analytic function divided by like z over some k or something, which means we call this the pole of order k. It means in your pole, you have a certain degree to it. Okay. It means you have a pole, but it has something power. It means it is not z minus a only. Now you have z minus a to the power something. Okay. Fine. You got it? Or you need some further explanation? Or you have give another formula, but I think it is better you can remind it this way, because if you, it is pretty much easier to calculate, because that's how I remind it, because you can, it is in terms of residues and so on, it is pretty much harder to remember. Or else I think you can have something called limits also. You can either remember, I think in your handouts there's something, some equations, there's some sort of like you can have your function like something like you can have your residue for some sort of limit thing. I think it is not much like it is, you can anyway remember, but the main idea behind the residues and the Lorentz series is you can evaluate a derivative of an analytic function using the integral of form if fz over z minus a to the power n dc. So whatever you have to do is, if you given some function, okay, something like you have some denominator and you have something like is it a or something like some sort of this. First, partial fraction this function in order to have something like this. You have something, you can have something in the numerator and z minus a1 plus from an z minus a2 and so on. You can only keep one pole in your denominator if you want to calculate, or else there's some easy thing you have to do. So, or else you can do some nice trick. Let's say you have something like evaluate something like this. So we have to evaluate. I draw my contour first. Let's say this is my 1 and this is my 2, and I have to evaluate some integral over this contour. Okay, so my function is something like gc is over some fz some analytic function over z minus 1 and z minus 2. So then what will I'm going to do is, so I can do is actually when we evaluate this integral, I can do very smart thing. So what I can do is I can get this thing is gc. If I want to evaluate this integral over this curve dc, what I'm going to do is I'm thinking of, I'm taking two contours, something like this. I take one contour like this and I take another contour like this to the same direction. Then I can write this thing as, look what I'm doing. My contour 1, let's say this is C1 and this is C2. This is my C1, and if z over z minus 2, this is in my denominator because this is analytical, because if z does not equal to 2, this is not going to infinite, divided by z minus 1. dz plus C2 fc over z minus 1, okay, divided by z minus 2. Now what will happen? You can straight away put z equals 1 to this to get an answer. You can straight away put z equal 2 to this, get an answer. If you have some polar order, some sort of like 3 or something, you can use this formula to get the answer, because you know this is, in this case, this function is apply it as your analytic function, then you can differentiate it and substitute your pole value and get the answer for this integral using this formula. Actually, this is the one I'm using because I'm not using the limit technique. It is like pretty much like you can most of the time you can forget it otherwise. So then what you can have to do is actually you can most probably use this formula to evaluate this integral. It means you have some analytic function and you have pole of order n, because your analytic function is dependent on your loop. Because if you consider this loop, this z minus 2 term is not going to be a pole because it is in this another loop, right? Because if you add this loop up, add this contour integrals up, this line is going to be cancelled out, because in one loop you go in this direction, another loop you're going in this direction. So these two will be cancelled out. So what we're going to do is your contour will divide into the poles of the complex numbers reside on this complex plane. You got it? Or you need some further explanation? Hello? Hello? Samantha? I just go it there because that's what about complex analysis is most of the time. And I will explain, I think there is something called you have a limit of this function, right? I will expand you this. It means actually you can do something like this. I think it is a certain formula for this. Let's say if you have something like this integral, right? You have to, let's say you have previously you have fn is equal to n factorial like 2fi into fz divided by z minus a n factorial n dc, right? This contour integral. It is some contour which is containing this complex number a. So you can simply write this thing as something like this. So what is my f is? Let's say this is my function, right? This is my function. I write into the factorial 2fi into the contour integral gc dz. I simply write this as gc. So I know this is equivalent to fn c. Okay. So what is fn? Fn means I know my fz is equivalent to z to the power a to the power n times gz. Because if I multiply this thing by this guy by z to the power z minus a to the power n, I will end up in fz. So then I can do fn z. I can differentiate this thing by n times z minus a to the power n gc, because this is equivalent to fc. Okay, so I can set my limit to z to the a, and I will end up the desired answer f to the power n a, because I know if my derivative is continuous, if I send my limit to the a, I will end up this answer, because this is equivalent to differentiating fz n times and sending limit to the a, or substituting z equals a. So this is actually one way of evaluating these integrals. So actually you don't need the meaning of the word residue to evaluate this integral. What you have to do is you need to figure out your contour and what is the pole, what is the complex number inside this contour which is restricting evaluating this integral. If you have something like a, if you straight away find it out, you have some factors, because definitely there are going to be some factors in your case, some factors z minus a or something in your denominator. Please look what are those things which are going to be poles inside your contour. So then you can evaluate this integral separately. Fine. Hello. Now what will happen if you have this type of thing? I will explain this. C, fc, dc, and you have some integral divided by z minus a, okay, or something like this. So what will happen? You have this your complex number a outside this contour. Then you can clearly have this integral going to be 0. Okay, this integral is going to be 0. Why? Why is going to be 0? Because if it is analytic, right? Let's say this is some sort of like contour function. If gc dc, this is going to be analytic function, right? So you can straight away you can write some you can write actually gc, and you can start from some point. Let's say this is point a and return to the point a. Then you evaluate this integral, you will end up in 0. This is a fundamental theorem of calculus, right? If you integrate your analytic function over loop, and this is actually this no hole inside this thing, actually you can straight away say this integral is going to be 0. Fine. Hello. Fine. Hello. Okay. Hello. Fine. Hello. Is it okay or you need anything to add? Because this thing is actually, let's say you have, because sometimes you have something like if z is equivalent to, let's say z minus a something, right? So then z minus a cancelling out, and then it will become some analytic function, and then the integral going to be 0. So this type of thing you can straight away say it is 0. But if you in exam, probably you will have to actually one time of question you have to do is in complex analysis. It's nothing but you can get something like to prove how Cauchy-Riemann equations come, then you can have to show what are the analytic function and how it is analytic function, or if it is analytic, so you have to show that Cauchy-Riemann equation now are still there, and then you have to use some residue theorem and get the Laurent series. That type of problem you can get. I don't much think there's be some question from harmonic functions and so on. Actually, these questions are there. I think it will be pretty much hard to handle sometime because it is you require more knowledge. But I think definitely most of the time in our case, we have in complex analysis problem, we have one problem to use Cauchy-Riemann equation, then we have to use residue theorem to calculate some integrals. So that are the most of the thing. Basically, the harmonic function, those are things actually they have some very basic things when if we do something proof for classes, that's what the thing we have. So anything you need to add? Hello. Hello. Anything you need to add? Or do you have anything to ask? I think there are a power cut going on. I think Sundar Siribarani. So if there anything to add or you have anything to ask, you can ask. I think those are the two things actually I don't know, want you to overwhelm this day before the exam, right? Otherwise, you will gonna be like or exhausted. Please just remember this Cauchy-Riemann equation. The important thing to remember this thing is you don't have permission to go from here to here except some conditions. I think they are in the handout. They will probably explain in the theorem. So you have to defer. It is you should be have these two things to be continuous. And also I think you need to have some boundness on this function as well. And also sometimes if you using this Cauchy-Riemann equation, then you second most important thing is that evaluating these integrals using this residue theorem or this complex type of integral. It's actually residue. You can use this integral. Actually, it is basic idea behind this integral. It is you call sometimes residue. Residue is nothing but just give a name for some side of this. If you have some function, if you have some contour, which has pole inside the pole, which has some pole A inside this contour, and then we're going to integrate this thing, and you will end up, we call this the thing just a name, a residue. But the idea behind this, just how to evaluate this integral is nothing but this idea. You have some analytic function in the numerator, and you have some z minus a or something which is which you takes a function value to infinity when you are z equal to a, and then you call it a pole, and then you evaluate this contour integral, and you can easily show that it is equivalent to your analytic function value at a. Okay. Is it fine now? You need to ask anything else you need to ask now, because that's are the most two important things as I believe. So if you have anything to doubt in curriculum, or you need to anything to clarify your any type of problem, so you can ask, because I think now you need to prepare for the exam. That's why I straight away put these two things in, because these are the things most of the time you will get a problem in complex analysis question. Otherwise, I think you will get some problems like in complex functions and complex mappings. Don't worry, please keep in mind that complex function is nothing but you have some function, right? If C, it is equivalent to some function, okay? It can be a complex number or anything, but your Z is Z equals X plus IY. You can same thing, you can think it as X plus X fxy, where your function value is something like, let's say you have fz is equivalent to Z plus 1, and then you can simply write this as something like fxy, which is equivalent to X plus IY plus 1. Okay, so actually this is actually, then this will become actually bivariable function. Now your arguments are real numbers, but your function value itself is a complex number. So actually you can always see your complex functions as a multivariable function which are having complex values as function values. So this is no difference between multivariate calculus and complex analysis. So if you encounter some problem inside your paper, please clear in your mind and use whatever you do to the real functions, because it is nothing but this only constant I in your complex function. There's nothing wonder here. So you can use any function, the derivative rules, limit rules, anything, treating this as just a coefficient or something. Okay. So anything you need to add? Or you need to ask? So you can ask, because I know it is like tomorrow's the exam and you need to have a lot more thing to do. So is it okay? So, or you need to have anything to ask? This actually, that's what about complex analysis. So if you have a difficult part, you can ask now. Hello? Anyone? Or if you didn't get it, I can explain it again, right? Because those are things most probably, if you can evaluate this integral, this contour integral, and evaluate the Laurent series, because it is actually, you can get a Laurent series from these things pretty much easily. So you can get to the question. And also, if you know how the Cauchy-Riemann equation coming, how to function is analytic, you will also get through that. So if it is fine, I can wind up, or anything. If you have any problem, you can ask me now. You can ask me now. Okay. Hello. Hello.
Okay.
Okay. So I will, so if there's no question, I will end the session. If you have encountered any problems, please drop me a message today's night. I think most probably I will like wake up around another like few minutes, like another half an hour. Oh, and also in tomorrow morning, please message me before, like you can send the message in the morning as well, but I will be replying around before after 10, right? Because I have some yoga sessions in the university, so I cannot access the phone between 8 and 10. But I will reply after that. So if you have any problem, but and also if you want any clarifications, so you can find, I think I will told you to one of your colleagues when I meeting the university today. So you can, if you want to complex analysis, just the Wesleyan University. Just search this in YouTube, and there are some videos from Petra Bonford Taylor. These are pretty much good. Actually, these are like some 5 or 6 20-minute videos. That's are pretty much good with the animation. She will explain pretty much nice. So you can get the complex analysis things pretty much good from these videos. So I think you can go from here. Actually, these some videos from Coursera post, but it will available on YouTube. So you can clearly search this thing. Also, you can watch my Kuppi video two, which I done for 18 lectures. So there are actually these things like just going to be actually I got this type of time to do these things, but there will be more than enough for you guys. And also, if you want to get to know how these thing limit definition extend to higher dimension, how you get the existence of limit and so on, watch the videos. I think I put some lengthy message like how you extend the limit definition to higher dimensions and so on, or what is the idea behind the gradient. So you can watch that if you want. But I think if you know how to what are the Cauchy-Riemann equations means, and you know how you evaluate these contour integrals, you are good to go. To at least you can score around 60% to 50%, 50% to 70% marks for the complex analysis problem, unless they you can actually score around 90% unless they give something around harmonic functions and so on, because they are pretty much hard things to evaluate. It is like you will need more calculations, but it is time is not sufficient to do that. Otherwise, I can do that, but if I do that, sometimes I will go missing, and also you will go missing. So it is better to teach this thing, because actually at least you can do these things. Actually, do these two things, and what are the analytic means and so on. You can probably do a good job. So that's it. So if anything, any question is having, you can ask, or otherwise you can any question you can ask. Actually, there are some problem more like these, what are the types of problems come. Actually, I don't know, but I can pretty sure there will be a question from Lorentz series and these contour integrals, and also there will be a question from Cauchy-Riemann equations. So without those three things, I don't see with there will be a complex analysis question. So there will be some significant amount of marks for these three parts, and this is pretty much easy. There's two ideas, Cauchy-Riemann equations, how they will come. Sometimes we can ask the proof, right? It means then you have to go from in imaginary axis direction and real axis direction, and you can evaluate the derivative along those two directions and make them equal. And you can have uh, you can have evaluate this integral. It means you have some contour integral and you have a point inside this contour, and they will have to evaluate this contour integral. So then you need to have these type of results which I've derived, and also you can use this thing to derive the Laurent series. This is nothing but actually this formula is already given in the Taylor series. In terms of nth derivative, you will put this integral and evaluate from this formula. Okay. So straight away you will get the coefficient of, let's say actually this is coefficient of in the Laurent series z to the power a minus n coefficient. This integral is nothing but this coefficient of z to the power minus z minus a to the power n. So in sometimes this coefficient can be negative because sometimes you have chords order more than one. Then you will have negative coefficient as well in the Laurent series. Let's say you have some function like f z, this analytic function, and z to the minus a to the power 3 or something. Then your n value can go up to minus 2 as well. Okay. Yeah. Yeah. So you can have minus 2 as well. So if you evaluate this integral, so I think your n value can go up to actually it is going to be your n value can go up to actually minus 3. You can n value can go up to minus 3 or something. You can just have to get GS, and let's see what is the value. Is it to the power minus a n plus 1, and this should keep become that least value. This will you be left with z minus a in the denominator. So you can find what other value is. It means if z minus 3 is n plus 4, so you will have n minus 3. So if you write the Laurent series, it will go from minus 3 to infinity plus infinity. Sometimes it can start from minus 10 or something, but it depends on. So it doesn't matter. It means you just write your function. Let's say your gz is nothing but analytic function over some z minus power k. You just write this thing z to the power a n plus 1. It will become fc divided by z to the power a n plus k minus 1. So n plus k plus 1. So if you have n minus k, you have the this power will become 1. So it is your least power. It means your Laurent series goes from minus k to infinity. Okay. So it means your Laurent series start from the minus value of this the Paul's order, and it goes to the infinity. So that's the thing you need to remain, and you can easily evaluate this coefficients using this formula. Or you can to evaluate the coefficient, we have to simply disregard this term, because in order to get the coefficient, you will simply divide it by n factorial. Okay. Hello. Hello. Fine. Hello. Any problem you can ask, or otherwise we can wind up. Or any problem you can ask, right? Hello. Okay, so I will stop the recording. So you can have any problem, you can message me. I think I will be around some another half an hour to 1 hour, or you can message me in the morning. Also, actually, pretty much, I think, sorry if I go too fast, but I will do, because you guys telling me that actually you guys don't like understand the concept, or it is pretty much hard for you guys, but it is nothing but if you know these two things properly, actually you can get a significant amount of marks. Actually, I think there is some information on my previous book videos, as well as I suggested to you in the videos. I will send you those YouTube videos links as well, so you can go through that. Well, like, this not much actually. If you go through it, it's around 3 to 4 or maximum 5 of videos of 20 minutes, so you can easily go through. Thank you. So if you have no questions, I will end this thing, and thank you for joining, and I will wish you good luck for the exam. I think unfortunately some guys left due to the power cuts and so on. So if you have any problem, you can ask, right? Or even after the Kuppi,